Okay. I think you're ready. So today I thought of having very graphic slides or something like that. But at the end of the day, I ended up writing my lecture notes, and I will try to write them so that it would be a little bit easier for you to follow. So in this course, we talked about geometry, and we talked about, by the way, if I could see your faces, it could be great. But so we talked about Laplacians, either in 1D, in 2D, wherever. This is how you denote them, either as this delta function or like that or like that. And this was the Laplacian. Now, in signal processing per se, the justification of using the Laplacian came about from the following problem. Assume that I would like to represent, we talked about it, assume that I would like to represent a function by finding a basis, a set of basis functions psi, so that the projection of this function onto this basis would give me in this representation the best possible way of representing a function. And in this truncated by k basis, I would like to represent my function in the best possible way. So the best possible way is finding this set of basis functions psi I, and I would like to maximize over all possible functions that belong to some family. Now, in the case of, and this was assumed that this is what you would like to do in order to get your basis. And now you're searching over all possible bases, either in a discrete setting or in a continuous setting. And it appears that if, for example, you would limit your functions to belong to all smooth functions, then the space in which it would be optimal to represent your functions would be nothing but the eigenfunctions of the Laplacian. So taking the Laplacian operator and writing something like that, and then ordering these functions in a corresponding order so that lambda I would be the smallest one, sorry, lambda 0 would be the smallest one, actually it would be 0, etc. Then this would be the best way of representing functions such that the gradient of these functions are somehow bounded, okay? So this was the reason for looking at the eigenfunctions of the Laplacian. They are the best basis to represent that are needed in order to represent smooth functions. These are kind of smooth functions, and this is great. We know that if we would like to represent functions, and all we know about these functions is that they are smooth, we have a perfect basis to work in, again, in L2 sense. Then we all know that if we have some further knowledge about these functions, then, for example, let's assume that I know the autocorrelation matrix of these functions, then what we have is a somewhat different problem. Let me try to reformulate this problem. So now I have a family of functions, okay? So now this family of functions, let me write them as some index that runs between 1 and capital N, is a set of functions, and I would like to project my functions onto a different basis, okay? And so this would be a different basis. And I would like it to have the best possible error, say in L2. So what would be the solution for this problem? What would be the optimal basis for this problem? We talked about it. It would be, so you can see the similarity between these two problems. The top one was looking at some operator such that the function belongs to this family. And the second one would be find a different basis so that the function belongs to a given set of, for example, of a given set of n such functions, okay? And here I don't want to write much, but assume that you would also like to, well, let's leave it like that, okay? So the other one would be nothing but the PCA. So here we assume that somebody is giving us something, a very general notion, and here we have some notion of samples from my family of functions that I'm looking at, and we can see the similarity between these two guys. I mean, here what we need to do is compute the outer product. So we need to sum over the outer product of my fj's. So if we think of fj as a vector, then we just have to put the first one like that and the second one like that. Summing over all of them, what I would get is nothing but the autocorrelation matrix. Okay. We also realized that in order to get to the Laplacian, what we can do is minimize, for example, the Dirichlet energy, something like that, from which we show that the Euler-Lagrange equation was nothing but minus the Laplacian of f should be equal to 0. And using it as a gradient descent process, we had that f of t is equal to the heat equation. Okay, this was the heat equation. This was the most efficient way of taking a function and reducing its Dirichlet energy in the set of all possible functions in a gradient descent fashion. Then we argued that everything here works on flat domain. What do I mean by that? I had my function, which is defined on the t or the x coordinate, and everything in the x coordinate remains in the x coordinate. These are universal coordinates. But now, what happens when my function is defined on some curved domain? Okay, so this is now my domain on which the function is defined. If it's one-dimensional, that I can still use t in order to parameterize it, but assume that now I can modify t somehow, and in 2 dimensions it becomes even more interesting. Then now, rather than dealing with the Dirichlet energy, I can think of what would happen if I, for example, would like to minimize the area of my manifold. Okay, so it was if I had a 2-dimensional manifold, I looked at the determinant of the matrix, and then this guy is actually equivalent to minimizing the area of my function, and the Euler-Lagrange equation here was applying the Laplace-Beltrami operator. Now I'm adding this metric here that operates on my surface, on my manifold. Okay, this was the Euler-Lagrange equation, and applying it in a gradient descent fashion gave me something which was nothing but the mean curvature flow. Okay, so sorry, the mean curvature flow. Okay, this was the vector. So here again we got the Laplacian, but now in a geometric fashion, and exactly as before, when we take the eigen functions and eigenvalues and corresponding eigenvalues of the Laplacian, what we got is a best way of representing signals on my curved manifold, okay, in L2 sense. So everything we have done before can now be modified to some metric here, and then so I added some metric here, and then the Laplacian would be the Laplacian of Beltrami, the Laplace-Beltrami operator, for which we know that it has these nice properties. I mean, it has a mean curvature flow like a property, and decomposing it gives me a convenient way of representing signals on my manifolds. And specifically, what was of great, I would say, of vital interest to us, so this would be 3, was manifolds that look like 2-dimensional surfaces in 3D. Okay, so this is my S surface, and this was my Q surface. So I have these 2 manifolds that are given to me separately. So think about them as the different samples of Ronen ECG or EEGs from the brain, but here it's embedded in R3. And in fact, this is a 2-dimensional manifold. I mean, it's a 2D manifold, which is called surface. And the question was, how can we use the Laplace-Beltrami operator in order to try and find and define some distances between these 2 surfaces? Okay, how do I define a distance? And we resorted to the Gromov or the Gromov-Hausdorff distance. And as a side note, I would say that you can define the Laplace-Beltrami with the metric itself, but you can actually define it with what we denoted as the scale invariant metric. So just to remind you, the regular metric was just GIJs, and the scale invariant ones were nothing but multiplying the Gaussian curvature by the GIJs, and then we got a different operator. Then what we showed, this was the end of my one before last lecture, was that if I'm now taking the surface S and I'm computing the Laplace-Beltrami operator, from which I'm extracting the corresponding eigenspace. Okay, so these were my thetas, my psi's. And I'm also using the scale invariant Laplace-Beltrami operator, from which I'm extracting the scale invariant eigenfunctions or eigenbases. Okay, so this is the whole basis. Then, using the functional map idea, I could do the inner product of one with the other, and we called it alpha ij, which was nothing but the inner product of psi I by psi tilde j in one of the norms here, assume G. Okay, and we could do the same for Q. So for Q, I had now it's a different Laplace-Beltrami operator. Let's call it Laplacian with respect to Q, and there was one which is scale invariant, which we call the Q tilde, from which now I need a different notation. So this was psi I, and this was psi I tilde. And again, the inner product gave me some, now it would not be alpha, but rather these betas, ij's. And now here, using the functional map trick, what I could do is somehow compute the permutation matrix. Okay, the matrix that connects between each point in S to each and every point in Q. Okay, so there was this magic of what I was actually doing is extracting this matrix C by taking the full matrix of all possible inner products and subtracting beta from it, and then the permutation could be approximated by nothing but taking the whole matrices, the full basis psi I times C, and here I had the full matrix phi transpose. Okay, this was a way of approximating the permutation matrix. Okay, how do we? And again, this was a 30,000 perspective on this lecture about how do we, at the end of the day, can approximate the Gromov-Hausdorff distance by using this decomposition into spectral domains. We'll get back to it in a moment, but before that, we said that in order to optimize for this guy, I also wanted to use the knowledge, Ronen mentioned geodesics, of geodesics here. So assume that somebody is giving me all the intergeodesics, all the interdistances between all points in Q and all points in red. So I have this D of all points to all points in S, and I have this other D of all points to all points in Q. And as a side note, I would say that these distances were computed by solving no other than the iconal equation. So again, we know that for distances have gradient which is equal to 1. So this is distance map. If we know how to solve this kind of equation, we can compute distance map. Specifically, when we have this G here, then we have distance maps on manifolds. And now what we would like to do is somehow compare this D of S cross S, okay, because I want all points, all distances between all points to all points in S, to D Q cross Q. And the way we did it is I mean, we tried many ways to solve this kind of problem. The first one was the classical scaling. Okay, so the first one took this D, and let's short note it as D of S, and we were looking for points, for a set of points in R 2, 3, etc. I mean, in finite dimensional space, and then the embedding was shown to be to include error. Okay. So here, do it either with TSNE, with MDS, classical scaling, whatever. If the original manifold was curved, then embedding into this flat domain also introduce error. And we tried also to do it with S of Q. So here we got these QIs that also belong to this same Euclidean space. And then we tried in this intermediate space to try to somehow rotate and translate these coordinates and try to fit them. In fact, what we did in the case of classical scaling, what we try to do is look at the eigenvalues of this double centering way of looking at these squared values of this distance, and these were nothing but the second order moments, of the canonical representations of S and Q. Okay, and when we compared between them, we could actually do something, but tell something about the similarity or dissimilarity of the surfaces. Again, at the end of the day, what we were trying to do is find the permutation matrix that would multiply my d of q, my d of s, so that it would look as much as possible as the intergeodesic distances d of q. And here I have the permutation matrix. Usually it's much easier to do it in L2, but assume that the metric now is not really important. And what we showed is that if we use this functional map idea of approximating P as phi, capital Phi, and now rather than C, let's call it alpha P. Okay, this is a matrix that represents a permutation in the dual basis. Okay, and now this problem reads, I mean, let's keep P for a moment and just write the intergeodesic distances as psi alpha S psi transpose minus, now I have, so this was my ds, and I do the same for dq. So dq was phi, now I have another alpha, it would be alpha q, and here I have psi transpose, and here I have P again. And if I now plug this P into this equation, I end up with minimization of something that looks like alpha P, alpha S. Usually these are small matrices. I mean, if the D was capital N by capital N, then this would be a much smaller matrix, small capital N by small n by small n, minus alpha Q times alpha P. Okay, so working in the spectral domain allows us to reduce the dimensionality of this problem into a much lower one, but it also introduces some problems. For example, some of the problems is the fact that if I look at my permutation matrix, it's a high frequency matrix. I mean, there is a delta function at each and every entry. I mean, this is what I would like it to be in the limit. While if I truncate the frequencies by which I represent it, if I would like a small matrix alpha P, then I somehow smooth and smear my permutation matrix. Okay, now this course has to do with learning, and these days there is no learning without neural network. Okay, and what we argued is that the big success of neural networks is the fact that you can have this nice local symmetry property that gave birth to convolutional neural network. So neural network either has this convolutional property, which actually talks about some local symmetries that we can exploit in order to have this nice property that can be used in order to reduce the large amount of parameters that we need in order to operate our images. Or it could be fully convolutional, fully connected. And Siri immediately woke up because I said sorry. So that this is something that we have seen in the functional MapNet. So this has to do with low dimensionality. So if the dimensionality is really low, I mean, if I have just 3 numbers, x, y, and z, I can x, y, and z that describe a coordinate, then I can use fully connected network, and I can lift this space into R1000. This is something that we have seen with PointNet. So the first example, there are 2 examples to this methodology of how to translate geometric problems where there is no CNN in the game into this neural network. So the first one was first take functional map, then what Litani did is introduce the functional map net. And what Halimi did is actually did the functional map net in an unsupervised. So it would be unsup fashion. Okay. At the other end, we have seen the point net. So just to remind you, the point net was this network that took X, Y, Z and lifted them into 1,000-dimensional space, and then folded all these points in this 1,000-dimensional space by just taking the maximum from each coordinate or the average of each coordinate. So our understanding that what point net did is something like computing moments allowed us to, I think we called it MomentNet, is somehow reduce the complexity of the point net method in order to achieve better results. So understanding the geometry, the axiomatic fashion by which data is represented, and how classical solvers were used in order to come up with solution, gave us the power to do something useful. Now, at this point, I would like to talk about something new. I mean, new to this course, which is classical in the sense of, and it has to do with the image denoising. And it is a completely axiomatic method, but if you understand this axiomatic method, I would say that you can do the same trick with the FMNet in order to enhance the power of your denoising networks, okay? So the state of the art of denoising images is learning the characteristics of the noise and training a network to do something which has to do with, I mean, a sequence of convolutional layers with the nonlinearity in the middle. But the question is, what would happen if we now look at images from a completely different perspective, trying to analyze how an image should look like? And to that end, the reason that I'm presenting this topic is because it involves the Laplace-Beltrami operator. I mean, there would be a metric involved inside. And if now let me give you a spoiler. At the end of the day, if we look at the evolution of modern image denoising algorithms, there was a sequence of papers, one of them by Thomas Pock, that actually took this idea of training for the metric and was able to, in fact, get state-of-the-art results with something similar to what I'm going to show you in a couple of moments. And along the way, there was Aaron Wetzler that also did something related, as well as Petros Maragos, that took this kind of diffusion of images into patch analysis and was able to show state-of-the-art results with a related mechanism. So I mentioned that we will start from an axiomatic image formation model. Image formation model. Remember that when we started this course, I told you that if I'm looking at an object from far, far away, so this is me observing, looking at this object, and now I assume that this object is a perfect diffuser in the sense that there are no specularities. Then the image that I'm looking at would be the color at each and every point here would be proportional to the inner product between, so there is light here, between the light source direction, so this is the light source direction, and the normal of the surface. This would be the normal of the surface at each and every point. So the image would be nothing but I of x and y was nothing but the inner product between n and L. Now n, the normal, is a number that changes as I travel along my surface, and L is a constant value that depends only on the light sources. If I'm just taking an image, then the light source would always be the same. There is something else here which I didn't mention, and this is the fact that if I'm looking at the red image, so this was true for the blue, the red image is exactly the same. I mean, it would be exactly the same product, but there is this factor which I call which I call the albedo, which was different for the blue. It is different for the red, and obviously it is different also for the green. Now, if I look at an image, let us look at an image, and in this image I have one object, I don't know, an apple, a red apple, and another object, an orange. Then within the orange, this number would always be the same. And within the apple, these numbers would always be the same. The only transition that we'll have would be along the boundary. Okay.
Why they would be the same?
Because if I assume that my objects are that the orange is always orange and the apple is always green, then the albedo, then the color that I assign to these guys would always be the same. Now, this is true up to a point, because I can, for example, think about colors of specific butterflies that change from green to blue to white, and therefore the albedo is changing also in this kind of events. But roughly speaking, to most objects in nature, a specific object would have a specific set of constant albedos. Okay, so within an object, the albedo would all more or less be the same. The change in intensity that I would see would correspond to this part of the equation, would correspond to the what we call the shading part of the equation. So this is the color, and I assume that objects have more or less the same color, and this is the shading part. Okay, and again, what I'm describing here is a really rough image formation model. Obviously, when I introduce specularity, then everything would fall apart. And when I introduce objects where the colors, I mean, I can't see in my room right now, but if I would look at the objects where the colors are changing smoothly from one object to the other, then this model would obviously break. Okay, so what would happen if I would now take, so this would be the blue, this would be the red, and this would be the green. What would happen if I now take the gradient of the blue image? I mean, what would be the relation between the gradient of the blue image and the gradient of the red image, for example? Let's do that. I mean, let's take the gradient of the blue. So here, let's call the shading image I of xy. Okay. So the gradient of
it's supposed to be the same.
Again,
Right.
so the same up to
Difference in the albedo.
Up to the albedo.
Up to the albedo. So they should be parallel to one another. Okay.
Yeah.
Okay. So if you got it, then again, if I'm taking the gradient of the blue, it should be up to the ratio between the albedos. It should be parallel to the gradient of the green, and it should be parallel to the gradient of the red. Okay. Okay. So this property is a really important property in image formation model. This is called Lambertian or fully diffused images. So this is Lambertian images or image formation model. Because there was a painter, Lambert, who actually painted objects such that they are piecewise constant, but it applies to the real world as well. And I think that, it is often used. So this is a roughly speaking image formation model. Bear this in mind, okay? Now, in a moment, we'll come back to it. And it basically says that if we look at the gradient of the blue and the gradient of the red and the gradient of the green here, they should all be parallel to each other. Okay. By the way, just to as a side note, the same property should also hold along the boundary. So along the boundary, the red, green, and blue, since I have an abrupt change in intensity, should also be parallel. It could be in the other direction, but they should be parallel to one another. Okay, so this would also apply at the jump between objects. Okay, so now let's get back to our image formation, to how to process images. So classically, what people have been doing initially is minimize the Dirichlet energy. Why? Because they said, look, if somebody is giving me an image, what I would like to do is minimize this guy so that the image distance from some given original image, the norm between them should be equal to the variance of the noise. Okay, assume that I have Gaussian noise, and the only thing I know is that the variance of the noise is given. Then the original idea was to minimize this guy using this constraint, and you can either use it. You can either apply Lagrange multipliers or whatever. But this was basically the main theme behind classical image denoising, I would say, in the 90s and the 80s. Then people realized that if, rather than looking at the Dirichlet energy, you're minimizing just the absolute value of the function with the same constraint, you get better results. And the result was that rather than using something which was really greedy, what you need to do is go into something which is called total variation. And I would say the 90s until 2010 were dominated by algorithms that were applying this kind of filters. There is also a nice property to this minimization. It has to do with minimizing the level sets of the image, so it preserves, in some sense, the topology of the evolving. I mean, the corresponding filter. If here it was f of t equals f, the Hit equation, here the resulting filter was f of t equals the div of the normalized grad. Okay, rather than the gradient. Okay, and this is basically the mean curvature. This is basically the curvature of each and every level set, and you can show nice geometric properties about this evolution. Now, what happens about color images? I mean, what happens if you take an image f of xy and you just add a tilted plane to this image? If we do that, then the level sets of the image, I mean, if we think of an original image that was a dark object on a bright background, and this is how the original level sets look like, then if we add this kind of tilted plane to this image, the new level sets would look something like that. I mean, probably something like that. So preserving the property of level sets is not such as a property that we'd like to preserve. The question is, what should we do with color images? Okay, so for that end, we'll go into physics that were operating in the 18th and the 19th century. And that what they were trying to do is somehow analyze color perception in the human brain. So they were trying to take our understanding of colors and try to fit a metric, a GIJ, to our understanding of metric. Now, there have been many Helmholtz and McCann and others, and I do not like to get into the to this whole theory, but let me just give you something which is really, really oversimplistic, which says that our sensitivity to color, let's call it S of color, is equal to nothing but the change that we see, that you observe in the red color, plus the change that we see in the blue color, plus the change that we see in the green color. This is obviously an oversimplistic way of looking at the human perception of color, but it has to do with something. By the way, Helmholtz was playing with that. Schrödinger introduced some notion of color perception, and many others. Now, okay, let's accept that the manifold, that the human perception of color is given by this metric. In order to start and denoise images, what I need to do is look at a point and look at the neighbors of this point and somehow average between them. So I have to add to my color something that has to do with the spatial X and Y direction in the image. So let's do the simplest thing that people are doing in physics and add an arc length. So let's define an arc length so that we add the dx square plus dy square plus some, I don't know, some coefficient beta that multiplies the color. Okay, so this would be the color scale. And now we are working in this hybrid dimensional space where the space in X and the space in color play an important role. So now you can think of an image. You can think of an image, assume that this is my X and Y coordinates. And I can now think of the three colors as three manifolds, but you can think of the image as a manifold, as a two-dimensional manifold. It would be given by X, Y, and B of X and Y, and green of X and Y, and red of X and Y. Okay, this would be my image manifold. Now I know how to represent arc length. So from the arc length, I know how to extract a metric, Gij. Okay, we know how to translate the Gij would translate between way of measuring distances in the X and Y coordinates. I'm going here the X and the Y, and translate it onto the surface by this bilinear form that we used, and we called it Gij. Okay, so now my metric would be nothing but, my Gij would be nothing but 1 plus, let's do G11. It would be 1 plus Rx square plus Bx square. B, Rg, and B are my red, green, and blue images, and green X square, okay? And G12, for example, would be 1 plus, sorry, not 1. It would not be a 1 here, would be Rx times Ry plus Bx By, etc., plus Gx, Gy. Okay, so this would be my Gij. Now, the moment I have arc length and I have a metric, I can define area of the image manifold. And remember, there is also a beta here that I failed to mention. So there is also this beta here that tells me how the X and Y coordinates are related to the red, green, and blue colors. So minimizing the area of the surface would give me nothing but, we know what is the minimization of the area. It would be nothing but the Beltrami operator operating on my manifold. Okay, so it would be R, G, and B. And now I should have also modified the X and the Y, but now I'm fixing the X and the Y. Okay, so R, G, and B. So if, for example, I would have taken beta to be really, 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 really large, which means that the one would have been really, 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 really small compared to the RG and B, then what I'm looking at is at a two-dimensional manifold in the RGB space. And this flow would be nothing but, what would be the flow of a manifold where the Laplace-Beltrami operator is operating on this manifold? You should know.
The heat equation?
Again?
It's the heat equation?
So it's not the heat equation, but rather the geometric heat equation. This would be nothing but the mean curvature flow, okay? But in this crazy space of RGB. So if, for example, I would have plotted the blue, red, and green space, and I would look at the image. So now I'm looking at the image where it is here. So it would be a really complicated surface intersecting itself, obviously. But if I zoom in, at each and every point, I have a normal. And at each and every point, since I know how the points are connected to each other in the image plane, I know how they should be connected here. I have a normal, and I can compute the mean curvature vector. So flowing the image according to this vector would indeed give me a denoising effect. Now, if I would look at the structure of the Beltrami operator on the image, it would look like that. Let me show you how the, if I would look, sorry, not at the Beltrami, at this term. Okay, it would look, so the integration over G, du dv, would have the following form. It would be 1 plus beta squared that multiplies the sum over all the gradients of the red, green, and blue. Let's call it I, where I is R green and blue, okay, plus sum over all the cross products, all the inner products between gradient I and gradient, sorry, ij. So this would be the, sorry, see here it should be the outer products, not the inner product, but rather the outer products. Squared, and there is a beta to the power of 4 here, and there is obviously this kind here. Now let's zoom in and ask what happens when beta goes to 0. What happens is that I would get again the total the Dirichlet energy. Okay, I would get something that approaches minimization of each and every element squared. You can show it quite easily. When beta is relatively large, what would happen is that these two terms would be insignificant, and the first term that I would like to minimize is this guy. Now let's zoom in at what is going on here. Let's look at my image, and I'm now looking at my green apple, and I'm looking at this point. Assume that this apple went through some noise. What happens here is that I have the gradient of the green image, the gradient of the red image, and the gradient of the blue image somehow distorted. For example, assume that your image went through some heavy JPEG compression or MPEG compression, then the gradients would have different directions. What this term is doing, I mean, flowing this image in the RGB space would basically tell my surface to somehow align and rotate these three gradients so that they would have the same direction. So this would be the first goal of my minimization problem. And if you remember, this was exactly, when we looked at the image formation model, this was exactly what we expected our image to be. Okay, so minimizing the area of the image manifold would indeed give me a good property. Now, let's assume that I have aligned the gradients of all red, green, and blue colors. The next thing that would happen is something that has to do with the gradient of the image, which is nothing but, if you think about it, an extension and a generalization of the total variation idea, because I have here squared and I'm taking the square root of, so it would be basically something that would minimize the total variation of the image. But again, the first part was causing the image to align its gradients, which is what a Lambertian image would look for. Now, this was a really cool idea. I presented it at Stanford. This was a joint work with Nir Sochen from now in Tel Aviv University and Ravi Maladi. I think now he's in McKinsey, but he used to be the chief technology of GE Power. I presented it at Stanford, and there were two interesting people in the audience, Tomasi and Menducci. And what they did is said, look, what is going on here without referencing, obviously. What is going on here is that Kimmel is defining ds squared to be dx squared plus di squared. Okay, and obviously there is also dy squared here. Let's define a filter that looks like that. Rather than taking my image, so this was my, assume that this is my image, and convolving it with a Gaussian kernel, which is what people have been doing classically, let's define the Gaussian kernel on the manifold itself. So the distance would not be, so the Gaussian kernel is e to the minus power of delta dx squared, up to some normalization, sigma squared, etc. And this is what I'm applying to my image. So what they said, don't put dx squared here, but rather replace it by dx squared plus dy squared, dy squared plus di squared. Okay, this was the new invention. Now, so again, each and every point is being now convolved, sort of convolved. It's not convolved because you also have the I here, and the value, the averaging value, has to do not only with the change in x, so delta is reserved to the Laplacian, but rather also, so let's look at this point. It would not be only the change in x, but it would also be the change in y. And in fact, what they do is they take this line here, and obviously there is a beta here, exactly as before. So taking an image I of x and sort of convolving it, but not convolving, I mean applying this kind of kernel. Okay, so it would be, I would not write the explicit, but let's call it sort of convolving, where E would be minus dx squared plus beta di squared divided by some variance, would be my new convolution, new way of filtering image. It's called this is called bilateral filter. And the question is, what is the relation between this guy and that guy? And that guy. Okay. So let me rephrase the question. On one hand, what I showed you is that if you take the RGB images and you flow it so that it would minimize the color area, we are doing something good. At the other end, there is this kind of kernel that is operating, on my image and is doing something similar. Now, from a bird's eye view, it looks as if it is unrelated, but it appears that if we look at the short time kernel of this equation, it would give you nothing but this guy. So looking at the bilateral filter from a differential point of view, if we look at let's look at an image again. And I have 3 minutes. Let's look at the image again. So I have my image. And now I'm looking at the local way of averaging this image with itself. So I'm looking at the Gaussian, and the tail of the Gaussian is not hovering, is not restricted to the x direction, but rather to the image manifold. Then what I'm doing is in fact that. So on the image manifold, what I can do is convolve with this kind of operator. Okay. So convolving the image with this kind of a filter or doing a bilateral filter are basically children of the same idea of minimizing the area of the image. Now, if you would say that the area is not the correct way for your modality, then you can change it. You can change it, you would get a different metric. In fact, you can learn the metric, and then you would get a different way of denoising an image. And if tomorrow you will have a different way of not color images, but something which is completely different, I don't know, electron microscopy or something like that, then you should be able to come up with an axiomatic way of penalizing your network to do better. So this is a way of training a network. Afterwards, what people have been doing is, rather than just looking at the RGB at each and every image pixel, they looked also at the neighboring points. So think about lifting the neighboring points as a vector about a point, and then diffusing in this hyperdimensional space, and then feeding everything into a network. And obviously, when you introduce this into networks, you would get much better results because your model is becoming richer. So in a nutshell, this is my story about the bilateral and the Beltrami filters. It has to do with the Laplacian. It has to do with geometric flows. It has to do with unsupervised way, potentially unsupervised ways of analyzing analyzing images. And just final comment about something that I talked about at the beginning of the lecture, and so sorry for bouncing back and forth. Remember that at the end of Talmon's lecture, of Renan's lecture, I started thinking about the relation of this part to parallel transport. If anyone would like to look into that and to, well, think what is going on here, we are respecting the geometry. We can work not necessarily, I mean, if you look at this part, it is indeed not the autocorrelation, but some outer product. And if instead we look at the autocorrelation, then there is a really nice relation between everything that is going on here. So again, replacing that flow with PCA and working in a natural way of looking at SIs and SQs could give us some way of relating to parallel transport. But again, it goes beyond the requirements of this course. So only if you like to go into the fine details while still being at 30,000 feet, be my guest and look into this problem. Questions? Faces.
Ronnie, I have a small technical question.
Sure.
If you could go right a few slides, the metric here.
Here.
Yeah, I think it was defined, if I remember correctly, by inner product, and then somehow you turned it to outer product, and this is why the gradient became parallel.
No, so wait. Let's look at GIJ, okay? GIJ, let's look at it formally.
Mm-hmm.
GIJ looks like that. It looks like 1 plus sum over the gradients. Here I have I red, sorry, IX red, I Y red, and here I have the same. So this would be on the red, green, and blue. And here I have the same, and here I have, so this was for IX, and here I have the same 1 plus the beta times IY squared, okay? Now the question, what is the determinant of this guy? The determinant of this guy, from the ones, I get the 1 here, sorry, from the ones, from the multiplication of the 1 in the determinant, I'm getting the 1 here. Okay, mm-hmm. From the multiplication of these guys with the ones, I'm getting the second term. So I'm not so sure if it's beta or beta squared. And from the multiplication of the rest with the rest, I'm getting the cross product.
Ah, okay.
Okay, so here I have the multiplication of the x's with the multiplication of with themselves, and this is how I'm getting that. Now, obviously, I would also get here the cross product. So this would be for all I and j, and the cross product of gradient red with the gradient red would be 0. Okay, so the inner product between gradient of the outer product between this vector to itself would be 0, because remember the cross product between two vectors is nothing but the area of the parallelogram that they span. Okay, and this is why minimizing the cross product is basically minimizing these parallelograms. Okay, Amir.
Yeah, thanks.
Ron, 2 questions. First of all, in the last slide, you mentioned the connection to higher order sampling and the left and the right, yes. So in the right, you wrote neural networks. Is this related to conditional random fields in a way?
Well, roughly speaking, everything is related to everything, but this has to do, this idea has to do with just patch processing. Okay, usually when you're processing patches, you would like to find the similarity between two nearby patches. Now, if I just look at this point and averaging with that point, then I'm not looking at the neighborhood. Okay? If I would also like to look at the neighborhood, then let's lift all these neighborhood as some function about this point, and all that neighborhood as a function about that point. And now diffusion in this neighborhood-like space is something that I can work with. It has geometric property. It has, now there is a fundamental difference between the bilateral filter and the Beltrami one. The Beltrami is a differential filter. So let me show you an example. If I have a signal that looks like that, then the bilateral, when averaging this point, would account to this point and probably that point, or that, when averaging about that point, it would look at this point and that point, if the distance is the same as being the same, okay? And it would consider them the same. Although there is this fundamental travel that you have to do between these two peaks. So, so the question is, what would you like to do? I mean, do you really care about the topology of structures in the image? If so, then use the Beltrami. If you don't care about the topology of object in the image, then use the bilateral. Use the approximated short time kernel. So again, linking between that and graphs, obviously, because you can think of each and every point as connecting to its neighbors, and random fields. And obviously, if you look at random walk of a point in an image, okay, then the probability of finding the random walker after you stop it after a bit of time would be nothing but a Gaussian kernel about a point, okay? Now you can think of this random walker walking in the image. Then obviously the probability of you finding this random walker at this point would be the diffusion, the Laplace Beltrami diffusion operating on the image. So yes, there is an intimate relation between the two, which obviously links between them in a really nice statistical manner.
Okay, and the second question is with regard to this, to the alignment between the directions of the RGB. Yes. So, in general, it seems to be always a problem while acquiring an image because of the mosaicing.
Yeah.
Right.
So in the mosaicing, let me just repeat for those of you who are not familiar with what is the mosaicing. In the mosaicing, usually if we zoom in into our sensor, it would look like that. Half the pixels, like a chessboard, would be sensitive to green. So these would be all the green sensors. Quarter of them would be red sensors, and another quarter would be blue sensors. And this is the image that is being acquired. And what we have to do is fill in the missing gaps. I mean, we would like to know what is the red for each and every point here, and we would like to know what is the blue. So we need to extrapolate or interpolate for the green, red, and blue. If you use only this as your condition when doing the interpolation, which means that you don't need to interpolate when you cross an edge, and you always like your gradients to be aligned, then you would get a really, really, really good the mosaicing algorithm, which has nothing to do with the image from. I mean, it has to do with image formation model, but it would be much better than any linear filter that you can think of. These days, since there is also noise in the game, and you have to denoise it, and each and every sensor has a different kind of noise formation model, then what you do is you have a neural network for doing the mosaicing. But again, if you use the Beltrami trick in order to do your interpolation, bearing in mind that this is a really important property, then you would get a really, really cool demosaicing algorithm. I mean, think about it. You interpolate for the blue here or for the red here, and what you force it so that you force it to have a gradient which would be equivalent to the indirection to the gradient of the green and the gradient of the blue. If you bear it in mind, I mean, I can show you, you would get much, much better results. But again, I don't know, there is recitation today, I don't remember. If there is, I don't want to.
Yes.
Yes.
Okay, so I don't want to take too much time. So you should give them 5 minutes to relax, but let me just show you some examples of how it looks like, how the mosaicing would look like. So what you see over here, this is the original image. This is after the mosaicing using bilinear interpolation. And this is where you weigh it according to what is going on. And if I just zoom in, you can see that with the linear interpolation, you get really terrible results. And with the preserving the parallel of the gradients, you get this guy. And this is yet another example and another example. So the mosaicing is indeed a really interesting problem to look at. And this property needs to be preserved there as well. More questions? If not, then thank you. You have 5 minutes, and then Yahweh would start her recitation.
Thank you very